Hello, welcome and good evening to another Let's Code MS-DOS episode. And today I want to introduce you to a graphics effect on the VGA card called copper or raster bars. You can find this on a lot of home computers of the 80s and 90s. The name copper bar stems from the Amiga actually, where the copper is a coprocessor on the Agnus chip, which allowed for very cool video trickery. But also the PC can do similar things, maybe a bit more simple, because let's face it, the VGA was a pretty dumb chip with not much compared to like the Amiga chipset. But things like this were possible. So you would get high color bars that move up and down, and you could like code a lot of them, and those were used usually, for example, like this in intros for BBSs or in cracked throws when you got pirated software or something. And it looks pretty neat. And the nice thing is it works in any VGA mode, even in text mode or 16 color modes, because the VGA has a digital to analog converter that you can tweak on the fly. And that's actually how this works. The old CRTs, the cathode ray tubes before the LCDs, were, let's start this again, were tracing the picture that was drawn from the top to the bottom and from left to right, more or less. And you could basically switch the palette during every line and hence get this very nice effect. And if we take a look at the VGA register, we already used the input status register at address 3DA, namely to synchronize with the vertical retrace. We already know that. We can read that port and wait until the bit flips. But there's also the display disabled bit, which is bit 0. And the documentation here says, when set to 1, this bit indicates a horizontal or vertical retrace interval. So you know when you just passed a vertical retrace, the next time the display disabled is set to 1, it must be a horizontal retrace actually. And when looking for this bit toggle, we can actually count the number of lines that we are already into the new picture that is displayed on the CRT. And that's what we're gonna do. For this to work in DOSBox, we actually need to set the machine type, because mostly the default DOSBox configuration will be SVGA S3, and this particular emulation doesn't emulate this register, so you won't see anything. For it to work, you need to switch to VGA only, which is what I did here on my Mac with the DOSBox 0.74-2 preferences. So I just write here machine equals VGA only, where it formerly said machine equals SVGA S3. You can also switch to Tandy mode for Tandy games to get Tandy sound and graphic modes, but that's not what we want today. We want VGA only. When you do that, the font changes slightly, but it's still recognizable. And so we can simply start coding. And first thing that we do is include our standard headers. We will need stuff from the DOS header for the port access. And we want a nice animation, so I want the sine or cosine functions, which are in the math header. And I probably need to read a character from the keyboard so that it doesn't get repeated. And maybe I want to print something. So standard I/O is always a good idea. The old C compilers, Turbo C is probably even older than the ANSI standard. So in 1989, the ANSI standard for C was made, but the 1989 standard doesn't include a constant for pi, because we will need pi for the sine function. So I'm asking here if pi is not defined, which will be the case on Turbo C. I'm just going to define it. as approximately 3.14159, and that's good enough for our purposes. You can add more digits if you want to. And furthermore, calling the sine function is expensive, terribly expensive, and we will do that every frame. So I want to avoid this. And the way I do it is I create an array, a byte array called sine, and I will make it 256 bytes in size. And I will create a function called init sine. And this will calculate a sine table, which is basically a fast lookup. I will get integer values because I need integer values instead of the float or double values that the sine function will return. We can have a look here at the math header. And there's all the nice functions. For example, the sine function, which takes a double and returns a double. And that's not what we want. Axis and radians, that is, it goes from 0 to 2 pi before the function repeats. And it returns a value in the range between -1 and 1. But I want something in the range of 0 to 255 because I take bytes. And this will be also our screen coordinate. So let's make a for loop. For I equals 0, I less than 256, increment I, and let's fill the table. So the element number I will be scaled to byte size. So I say something times 255. And what is it that we take times 255? Well, it's some expression divided by 2. And why is it divided by 2? Because we read that sine goes from -1 to 1, so I will compute something here and add 1 to make it always positive. So now it will be from 0 to 2. But that would be bad because then I would reach 510 here. So I divide by 2. This way I scale the function. This will be some kind of sine call. This way I will scale the sine function not from -1 to 1, but from 0 to 1. Make sense? And if I take that times 255, I get exactly a byte value and can implicitly cast it to an integer. I could also cast it manually. C allows you to make this explicit. So I could write something like this, but it's actually not necessary in this version of C. Later versions might warn or even put an error if you lose accuracy by converting from float or double to integer. Okay, so what's the value? Something to do with I, obviously. But I need to scale I. I goes from 0 to 255. So I need to scale it to the domain of this sine. So if I divide it by 255, dot 0, important, otherwise we don't get a fraction, I will have an input from 0 to 1. But that's not good. The sine goes from 0 to 2 pi. So I need to scale it by 2 pi. What I have now is a value that goes from 0 to 2 pi when I iterate over I. And then I put this into the sine function and I get something between -1 and 1, and I scale this from 0 to 2 and then from 0 to 1. Multiplying this by 255 gives me a discrete sine table with 256 entries, scaling from 0 to 255. Now this is, when I'm going to recall this, this will be a very fast sine lookup. So let's write the main function, because there's already one thing that we can do. And that is to initialize the sine function. And we will also have, as usual, some busy loop while the keyboard was not pressed. We do whatever. We'll see. Okay. Then we need a bunch of variables. So we need to count the number of frames, because the sine function will take the time as an input, basically. So the time is the number of frames. We could also call it time or t or whatever. But I'm going to call it frames. Then we need our copper bars, and I'm going to store the position when the copper bar starts. I'll make 3, red, green, and blue. You can make more, and then invent some color scheme for them. And I'm gonna store a delta, which is the speed of the copper bar that it's moving at. We can initialize those variables already. So we start at frame 0. Starting at a later frame will just change the starting position. And all the copper bars will start at the top of the screen, at the first row. So that's their initialization, and let's make the first copper bar fast. It will always move 3 lines at a time from step to step. Or not 3 lines, but 3 steps in the sine table. And depending on where in the sine we are, it moves faster or slower. Then this one takes 1 step at a time. The green one, it will be the slowest, and the blue one will be a bit faster. Okay, what else do we need? For good measure, we will have a few iteration variables, and I know that I'm gonna need also a variable for the current line, and we will need the color that we are computing, red, green, and blue. And I think this is all we will need. First of all, we will need to wait in every loop for the vertical retrace. So for that to happen, and because this is really, everything is here very timing critical, I will use the disable function. If you remember from one of the former episodes, disables all the interrupts, except for the non-maskable ones, which is fine. But so no TSR or anything can disturb us in our counting of the frames and the lines. Otherwise, the picture will get messy very quickly if something happens in the background. And don't forget to enable after the critical section. And our critical section here is waiting for the vertical retrace. And we did this already. So we read a byte from the input status register of the VGA. And mask it with the vertical retrace bit. And then we wait for the bit to toggle. So, okay, this is, oh yeah, I should probably put parentheses around that to make it better. Now we need to define those, but we already know that. Define input status was 0x3DA on color cards, on monochrome, but we don't care for monochrome VGA. And we also saw that bit number 3 is vertical retrace. So that is 2 to the power of 3 is 8. So that's the hex value 8. And the horizontal retrace, or actually the display disable, but we will call it horizontal retrace here, is bit number 0, so it's hexadecimal value 1. 2 to the power of 0 equals 1. Okay, we have defined everything that's here. That's good. And now we start a new screen. So we start counting lines. Every time we need to set this to 0, and then we will do a while loop, a do while loop actually, while y is smaller than, I don't know, 300, and so we have actually 400 lines available. However, I tried that and it will not work on real hardware with this many. So to stay safe, I will say 350 lines. That works fine on my machine. And yeah, you might try it depending on how fast your machine is, because you might actually skip some lines, even though we are trying to be as fast and efficient as possible here. So that's what we do. And the easy part now is to wait for the line changes. So this is actually pretty similar to what we had here. So we can copy this. So we'll wait for the line to finish, and this works in the same manner, but with a horizontal retrace bit as a mask. And we'll do the disable, the enable, and afterwards we can say, okay, we counted one line. That's fine. I think we have something, so there's the while. Yeah, we should probably indent this a bit better. Okay, this is good. But there will be something more to do here. Probably not here, but it doesn't matter much, I guess. So what will we do here? We will set the color. Oops. And let's write it here as well. Wait for horizontal retrace. Next line. Setting the color, you already know that. This is done by writing to the palette index register the color that we want to change, and we're in text mode, so we have a lot of black screen. So we will, I think I can press Alt F5, yeah. You see there's a lot of black when you run the program, so we will change the color black. This will look nice. And then you write out to the palette data register the colors. And we have red, green, and blue. And we need to define palette index and palette data. We already did that in the VGA video, and that's 0x3c8, so hex 3c8 and 3c9. Define palette data 0x3c9. We probably should take away the semicolon, otherwise we get weird errors from the compiler. 3c8, 3c9. Okay, that's all good and fine. We can set the colors, but nothing will happen because we're not changing anything. We have possible use of color before definition in function main. That's not good. Why is it complaining? Because I forgot to set it. Shall we set it? Color 0 equals 0. It's not strictly necessary because we will set it in a moment. But let's be nice. It happens only once. It runs, it doesn't do anything. You can't see that it changes the palette because we're not doing anything yet. But we can do now. And how does it work? So we are counting the y coordinates. So what we can do is we can say if the y coordinate is bigger or equal to our copper bar coordinate, and if it's also smaller than the start of the copper bar plus whatever height we take. And I'm gonna choose 63 here because that's a nice size for a copper bar and it makes easier calculating the colors. If it's the case, then we will set the color to some value. We will have a look what we put here. Let's say 33 at the moment. No, let's say 63, which is the maximum amount. Or else we will put a 0 here, because then it's not active. And of course we have to set this is fine. This is actually fine, yes. And when we do this, we will also already see a bar, which doesn't do much because we're not moving it. The Y component of the copper bar never changes, but it has to change. And that is after every frame, right? Because we have to count the frames. At the end of each loop in our main loop, we count the frames. 1 frame is done. And we can actually increment the, or we can read actually the coordinate, and we use the sign table for that. And the simplest way to do that is to use frame modulo 256, because we have 256 entries. This way we will get a nice smooth animation. It will go up and down and up and down, and obviously not to the bottom because we are only going 256 pixels down. So this is already nice, right? We have 1 copper bar without any shading at it, but it moves smoothly, so that's fine. And we're not using the speed, so let's also use the speed. So we multiply the frame times the delta. Now it should be faster. Yeah, this is a fast copper bar. And we can actually do this for all 3 copper bars. However, we will need to write this 3 times. We can make a for loop actually, but it's actually not good to do a for loop because this is timing critical, and every for loop has a slight overhead. So we will just write the code 3 times. But we can already set the coordinates for the other 2 copper bars, which is straightforward. Just change the indices and it will still run, but we won't see anything because we don't set the colors for the other 2 copper bars. But we can do that. Let's see all the 3 copper bars. So, very simple. Just replace the indices with 1 and 2 respectively. And we should see a red, a green, and a blue copper bar. Yeah, this is already nice. Pretty smooth. Of course, this is actually pretty hard to emulate. It's very expensive because DOSBox has to count and emulate the retrace and everything. But still, it's good enough. But now we want to add shading, right? Because this looks nice, but it's not as nice as we can make it. Because the cool thing is that even in text mode, we can display hundreds of colors. And that's what we'll do. In theory, what we can do here is just do Y minus copper 0. And this will already give us shading. You see that the red copper bar is shaded from black to bright red, but I want to make it look more round. So what I will do is, actually we can take this, and I had this second variable, right? I'm not using I currently. No, I can use the I variable. And I will call this I. And then, we make a ternary expression which does the following. You can write an expression like, is I less than 32? So that means we haven't reached the middle, question mark. Is I smaller than 32? Then do something, else do something else. And something and something else are now two different expressions. If we are smaller than 32, we just take I times 2, then it will go from 0 to 63 at most. 62 actually, but that's good enough. And otherwise we want to let it go from 62 to 0. So we just take 63, subtract I, and then also multiply it by 2. This way we will get a very nice red bar. The other ones are still looking flat, obviously. But we can just copy this. Delete that. Replace that. And then also replace that here. Delete that. And we should hopefully have nice copper bars. Look at that. So that's where I wanted to go. 3 RGB copper bars with nice round shading. And I think it looks amazing because this is actually text mode, this is not graphics mode. And it has pretty smooth animation. On a real PC with a real CRTC you will get this in 70 frames per second, and I think it looks awesome, and it's amazing that you can do this with this old hardware. And it should work even on a 286. We will have a look now on the 386, but I will capture it with my HDMI capture card. So it doesn't look as good as it would look in person, but so that you see that it also works on that one. Okay, so here we are on the 386, and let's just run the program. And as you can see, it looks a bit jittery due to the HDMI capture. It's not perfect, and you can see a little bit of artifacts because it's all analog here. You can see a bit of noise in the middle of the screen, but that's typical for old VGA cards. But it works, so even through HDMI capture on an old machine, this definitely works. So yeah, feel free to use this effect. You can enhance it, put other colors to it, and there's a lot more that you can actually do with the CRT registers, etc. But this will have to wait for another time. In the meantime, thank you very much for watching. I hope you learned something in this episode. Please leave a comment if you like this. Also press the like or dislike buttons, share and subscribe. And if you enjoyed this very much, you can also leave a tip on Ko-Fi or on Patreon, or just, support me by sharing and commenting. That's always very nice. Other than that, I will leave you to this, and I hope to see you next time. Bye.